given by Hailin, who will tell us about topics on coherent states and high-dimension operators in gauge gravity correspondence.
Thank you very much. Let me thank the organizers and the participants for the wonderful workshop. Today, I will talk about coherent states in gauge gravity correspondence. These coherent states can be created by operators involving operators with high conformal dimensions. The coherent states are widely used in various contexts of physics. In gauge gravity correspondence, there are different types of coherent states. Here, I focus on special types of coherent states, which have very explicit gravity dual descriptions. These are coherent states which have been constructed by Berenstain-Wang and Hogan-Wang. It has the following expression, for example. Here we can consider gauge theory, for example, angle 4 super Yang-Mills theory, as an example. We can consider a scalar field Z, and AZ dagger is the operator creating the Z field. And we have a n by n matrix coefficient lambda Z, which is the coherent state amplitude. This is the coherent state. Another new feature of the state is that there's a U, and the U is the element of the gauge group. The U can be interpreted in two ways. One way is that U acts on the matrix coefficient lambda Z. Another interpretation is that one can move the U onto the right of the AZ dagger, and the U acts on the AZ dagger. In the second interpretation, it means the state is gauge invariant. And this coherent state is also group averaged coherent state because of the U integral. It's the generating function of multi-trace operators because we can expand the exponent and view the lambda Z as the expansion parameter. The action of the dilatation operators on these coherent state bases simplifies because the action of the AZ operator on the coherent state behaves as the matrix lambda Z. And the action of the AZ dagger acting on the right on the bra state behaves as a lambda Z bar. So the action of the dilatation simplifies. And these states are also in quiver theories, in Coulomb branches, and in orbifold cases. For example, in the quiver cases, for example, we can have two gauge groups, UN1 and UN2. One can integrate over the two groups and obtain the group averaged coherent state. And the construction works for gauge groups UN and also SON and SPN cases. We can also have more matrices. For example, we can excite a Z field and also another Y field. Lambda Z and lambda Y are n by n matrix coefficient. And the state is a quarter BPS if lambda Z, lambda Y commutes, in which case the action of the anomalous dilatation operator on the state is 0. We can also have three matrices with three matrix coefficient, lambda Z, lambda Y, and lambda X. And the states are 8 BPS if lambda Z, lambda Y, lambda X mutually commute. The correlation functions of the operators and the inner products involve two-term and three-term HCIZ integrals because of the U integral. These coherent states form a complete basis. One can also use them in coherent state path integrals. We can insert intermediate states expanded by coherent state basis. We can also construct similar coherent states in the SL2 sectors. This include, for example, a Z field and a derivative D+. Plus is the light cone direction. And in this operator on the rightmost, there's coherent state excitation of the Z field. On the left part, there's excitation of the D+, because C plus CD dagger, A dagger creates D plus acting on Z. And the left factor creates D plus acting on Z many times. And the state generates multi-trace products of the form. This is a trace operator inside which there's many D plus acting on Z. These operators are similar to BMN operators and the spin chain operators. There are at least two limits. One limit is that these NIs are all big. Another limit is that the NIs are small, and some NI can be 0. In some cases, it includes near BPS states, in which case the non-BPS part of the energy can be smaller than the BPS part of the energy. The SL2 sector are also similar to the conventional QCD theory. It is also related to the Wilson line and the form factors. We can also consider cousin PSU 11/2 sectors by including 2 other fermions. And this sector also includes near BPS states. It is also relevant to the spin matrix theory, in which one can take a low temperature limit to include near BPS states. There are other type of coherent states with different interpretations. These coherent states have been constructed by Berenstain-Miller and by alternative methods by Skandaris and Taylor, and by Simon, Balazs-Subramanian, and the collaborators. Here, for example, we can consider trace operator, trace xk, and we can label them as a tk. They have a creation operator ak dagger, which creates a trace state. We can consider the weight k Hilbert space, which include multiple excitations of the trace state. We can consider the Hilbert space as decomposed of these weight k subspaces. The states can be spanned by the product of AK dagger to the exponent WK acting on the vacuum. There are coherent states which can be written as the exponential of the Tk with the coefficient lambda k. And these coherent states are related to the edge of the droplets. One can have a chiral field, phi hat. When the chiral field is evaluated on the coherent state, it gives the shape of the droplet edge. For example, the shape of the droplet edge can be described by the chiral field, phi theta. We can consider the mode lambda k coherent states. And the chiral field evaluated on this state gives the corresponding shape of the droplet edge. The chiral field is a displacement of the edge of the droplet, playing the role of a height function. For example, we can consider circularly shaped droplets. And the theta parameterize the edge of the droplet. This coherent state distort the droplet edge. We can also consider more general cases, for example, multiple annuli. In that case, there are multiple edges of the droplet. And on each edge, one can consider this type of a coherent state. One can also consider droplets with very long stripes. In this case, one can consider excitations along the edge of the long stripe. And in this case, the coordinates along the stripe can also be non-compact because the coherent state excitation is local on this direction. There's also other type of coherent states where we can generalize the coherent state by Berenstain-Wong, Hogan-Wong, by including fermionic counterpart. The first three terms are the coherent states describing ordinary dual ADS giants. And the actual terms are fermionic counterparts. The lambda ZC, lambda YC, lambda XC are three T by T matrices. And the chi is M by T auxiliary fermion. This additional part describes a coherent state of a Hall excitations, because one can consider the dual ADS giants as ordinary particle excitations and the internal giants as Hall excitations. And this state can have a particle-Hall duality, where the particle can be viewed as giants and the Hall can be viewed as internal giants. The correlation function and the inner products of these states involve a convolution idea. We can first compute the correlation function of the unintegrated operators. And then after we calculate the correlator, we can integrate out finally the auxiliary fields. And the integration over the U can be considered as a convolution. In this way, we can generate correlators of integrated operators by correlators of unintegrated operators. The coherence state parameters can also be packaged into a supermatrix form. Here, lambda is a m by m coherent state parameter, and the lambda c is t by t coherent state parameter for the Hall excitations. And we can arrange them into supermatrix. And lambda corresponds to the boson-boson part, and the lambda c corresponds to the fermion-fermion. And the coherent state can be written in a compact form using the supermatrix. The correlation function can be calculated by using HCIZ integrals and the super HCIZ type integrals, and the auxiliary SUSY integrals. This SUSY is the SUSY in the auxiliary variables of the bosons and fermions. It's not the SUSY of the gauge theory. In the case where the gauge theory does not have SUSY, we can still have this SUSY in the auxiliary variables. There can also be more matrices. For example, we can excite also Y and X, and we can package lambda Y, lambda YC into supermatrix in the same way. And these include eighth and quarter BPS cases. The coherent state can also be used for calculating correlators of the type HHL and HHLL. H is the heavy operator, and L is the light operator. Here we can use coherent state for the heavy and the single trace operator for the light operator. For example, we can consider the brass state capital lambda described by the matrix parameter lambda. And the cat state, small lambda, is a reduced coherent state. Lambda is a rank 1 subspace of the rank n coherent state parameter. This is to focus on one ADS dual giant. In the correlation functions, we can consider the single trace operator expanded. And in the gravity side, we can use the supergravity action and the string theory brane actions. And the calculation from the gravity side matches with the calculation from the field theory side. It has been performed by various authors using various methods. For example, it can be computed by using Schur polynomials of different representations, including symmetric representation and anti-symmetric representations. It can also be computed using other states which can be transformed by the Schur polynomial operators. For example, it can also be calculated by the coherent state. It can also be calculated by the method of Skandaris and Taylor using holographic renormalization method. These methods are alternative to each other, and they are equivalent for the answers. And also for another type of coherent state, describing the droplet edges, the relation between the chiral field and the shape can be also computed by our method of Berenstein-Miller, and alternatively by the method of Skandaris and Taylor. In computing the correlation functions, there are new saddle point method when evaluating the integral over the bosonic variables. And this is particularly useful for the heavy operators. And the full coherent state has a n by n matrix coefficient. There are many parameters. One can reduce the number of parameters by considering reduced coherent states. We can consider the rank P subspace of the rank n coherent state parameter. For example, P can be small. It can be 1, 2, or 3, describing few giant gravitons. The coherent states are also very convenient for adding strings. For example, we can have the BPS coherent state as this part, and we can also add a string, which is the W. And the string part, W, it can be labeled by BMN operators and the spin chain operators. For example, W can be a product of fields like Z, Y, X, and D+. There are special cases. For example, there are cases where the entire state is near BPS. In that case, the non-BPS energy can be small, relatively, compared to the BPS energy. And there are also cases where W can be a BPS string. There's anomalous energy from the interaction between the coherent state part and the string part, W. We can use the BMN analysis and also the dilatation generator to calculate the spectrum. There's another method for adding strings by using generating function. For example, the actual part is a generating function for adding strings. And the first part is the BPS coherent state. And here, one can consider WK as an added stream. We can take differentials with respect to the TK, and this brings the open stream. And this is equivalent to the to inserting stream. We can also insert closed streams. Before taking the trace, the WK is an open stream. One can also consider special cases where the TK is special and the TK is proportional to overall factor of the TK times the identity. And in that special case, you can pull the TK in front and take the trace of W. And that includes the closed string as a special case. Hence, we can study various configurations of the strings. Let me briefly summarize some new techniques involved or used in the calculation of the coherent states. One technique is the HCIZ and the super HCIZ integrals. Another technique is the auxiliary field integral and auxiliary SUSY integral. This SUSY is in the auxiliary bosonic and fermionic variables. Another interesting technique is the spin matrix theory, which takes a low temperature limit to include near BPS excitations. We can also use the techniques of centrally extended SU2 symmetry. It plays an important role in simplifying the spectrum and the S matrix. There's also techniques from the permutation centralizer algebras. These are also related to the basis of operators, including Brouwer algebra basis, global symmetry basis, and the multi-restricted Schur basis, which have been discussed by Brown, Haslop, Rangulam, Di Mello-Koch, and other friends. There's also interesting techniques from permutations and their related analytic combinatorics and algebraic combinatorics. The localization is an important techniques in the integrals. And we also have the coherent state formalism, which were developed by Berenstein-Miller, Berenstein-Wang Hogan, and also alternative by Skandaris-Taylor. There's new saddle point method, in particular in the correlation functions of heavy states and for the generating functions. When one integrate bosonic variables. There's also interesting techniques from the enhanced symmetry from coincident giants. Let me briefly mention some interesting outlooks. One outlook are the near BPS states. And they also include near BPS black holes. And therefore, we need techniques to analyze these states. And there's an important method of superconformal index by Huang and other friends. And there's also giant graviton expansion of the superconformal index, which one can expand it by giant gravitons. We can also study giants and coherent states in less symmetric theories, for example, N2-1 and N2 theories. We can also analyze the ABGM theory. These are highly symmetric theories. It would be also interesting to understand the less symmetric cases. Another outlook is a superstar and non-abelian T-duality. And this is related to Gaeto-Maldacena and have also been analyzed by Lozano, Nunes, and other friends. It would also be interesting to understand the relation between the collective field theory method and the coherent state. The parameters in the coherent states are the collective coordinates. The bootstrap is very useful here, because here one can also consider HHLL correlators and the HHL correlators and the spectrum of the H. These provided data for the bootstrap. And these are also related to fuzzball microstates and microstructures. The HHLL correlators are also relevant for the fuzzball, since the fuzzball state can also be viewed as a heavy state. And the fuzzball also has interesting relations and intersections with wormhole and island programs. Another interesting outlook is the code subspace, which have been analyzed by many authors. It is associated to the background reference state, and one can use the HKLL reconstruction to construct bulk local operators. And similar to the above states, one can also consider other close cousins, including Wilson and the line operators and the defect operators. Finally, it would be interesting to have a flat space limit. Here, one can calculate for the open strings and the closed strings. It would be interesting to take a flat space limit of the setup. Thank you.
Questions?
Hi, Professor. Thank you for the talk. I'm not really familiar with the field, so I'm wondering if you can talk a bit more about the context of your calculations or like how you can apply this into the, like what is special about coherent states?
The coherent state provide a new basis for the operators. And there's other bases like Schur polynomial basis and the multi-trace basis. They are related to each other by linear transformations. And they are the basis for the Hilbert space. And it's very interesting to understand the structure of the Hilbert space. Therefore, we need to understand the basis for the Hilbert space. In particular, once you have the basis, you can consider other states as the expansion using the basis state. For example, you can superpose two coherent state, and that becomes another state. So there are highly non-classical states, but they can, in this case, they can still be considered as a superposition of coherent states. So in some cases, it lacks the measurement basis.
Thank you for the talk. So in the last slides, you mentioned the BPS coherent state can be applied to problem of wormhole and island. So can you have more? Can you describe more about this? Thank you.
Yes, the island and the wormhole played an important role in the information problem, and the fuzzball is also very interesting for understanding the details of the microstructure. And these approaches are related to each other.
Any further questions? If not, let's thank the speaker again. And we reconvene tonight, I suppose. At what time?
Yeah, it's 8 p.m., right, at Bovinus. You have the map in the email from Humberto.